Hey everyone, and welcome back. Today we're doing something a little different, and I'm really excited about it. We're going straight to the source, the Bible of the field, really. We're deconstructing the very first chapter of Reinforcement Learning by Sutton and Bardo. If you're looking to get a rock-solid foundation in AI, trust me, this is the place to start. Okay, let's jump right in. Right out of the gate, the authors hit us with this beautifully simple idea. And it just makes sense, doesn't it? Think about how we learn, how a kid learns to walk, or how you learn to ride a bike. There wasn't a manual, right? It was all about interacting with the world. You try something, you fall, you adjust. It's this constant feedback loop of cause and effect. And that idea, that's really the philosophical soul of reinforcement learning. So, to really get our heads around this, here's our game plan. We're going to start with the absolute core idea. Then, we'll explore the world our learning agent lives in. After that, we'll pop open its toolbox and see what it's working with. Then, we'll see it all come to life with a classic game example. And finally, we'll take a quick look at the surprisingly cool history of where all this stuff came from. All right, so first things first, let's get a solid definition. What exactly is reinforcement learning? Okay, here's the formal definition straight from the book, but let's pull it apart. The whole goal is to learn a mapping, basically a strategy. For any given situation or state, what's the best action to take? And the whole point of that action is to get the biggest possible reward. But here are the two things that make RLs so special. One, it learns by pure trial and error. And two, it has to grapple with delayed rewards. Where the best move right now might not pay off until way, way down the line. And that whole trial and error thing creates this fundamental tension, what researchers call the exploration-exploitation dilemma. Just think about it. At any moment, the agent has a choice. Do I exploit what I already know? Stick to the tried and true move that gives me a decent, predictable reward? Or do I explore? Do I try something totally new, something risky that might lead to an even bigger reward I don't even know about yet? Balancing that trade-off? That's one of the biggest challenges in this entire field. So, to see how an agent even begins to solve a problem like that, we need to understand the world it operates in. The entire framework is built on this really elegant constant loop between our learning agent and its environment. And this is it. This is the engine that drives everything. It all starts with the agent taking a look around and observing the current state of its world. Based on what it sees, it picks an action. Then, the environment responds with two crucial pieces of information: a reward, which could be good, bad, or just zero, and a brand new state. And then, the whole cycle just repeats, over and over and over. This simple loop is the absolute foundation of all reinforcement learning. Now, for an agent to actually get smart from this loop, it needs a few critical tools in its belt. Sutton and Bardo tell us that pretty much any RL system is made up of four key pieces. And here they are: the policy, the reward signal, the value function, and sometimes an optional model of the world. Understanding what each of these does is absolutely key. So let's break them down one by one. First up, the policy. You can think of this as the agent's brain, or maybe its playbook. It's the part that looks at the world right now, the state, and decides what to do next. When we say an agent is learning, what we really mean is that it's trying to find the best possible policy. Next, we've got the reward signal. This is super simple but super important. It's just a number. At every step, the environment sends this number back to the agent. A big positive number is like a pat on the back. A negative number is a penalty. This signal defines the goal, plain and simple. The agent's one and only purpose in life is to rack up the highest total reward it possibly can over time. All right, now we get to the value function, and this to me is where the magic really starts. See, just chasing immediate rewards makes an agent short-sighted. It needs to think ahead. So while the reward signal tells the agent what's good right now, the value function is its crystal ball. It predicts the total reward it can expect to get in the future if it starts from its current state. This is what lets an agent make smart, far-sighted decisions, like sacrificing a small reward now for a massive one later. And last, we have the model. Now, this one's optional. Some agents have an internal simulation of their world, a model that lets them plan ahead by thinking, okay, if I do this, what's likely to happen next? We call these model-based agents. Agents that don't have this, the ones that learn just by pure trial and error, are called model-free. Okay, that's a ton of theory, I know. So let's make it real. Let's use the book's own classic example, teaching an agent to become a tic-tac-toe champion completely from scratch. So how in the world does it learn? Well, imagine the agent has a giant table, like a huge cheat sheet. For every single possible board configuration in tic-tac-toe, there's a score or a value.
At first, it has no idea what's good, so all the scores are neutral. Then it just plays against itself, thousands and thousands of times. After every single move, it looks at the board it landed on and updates the score for the board it just came from. If a move was part of a winning game, it nudges the scores for all the states on that path up, just a little. If it led to a loss, it nudges them down.
So this is the key. This is the learning rule. The agent makes a move from state ST to state ST plus 1. The trick is it updates the value of the state it just left to be a little bit closer to the value of the new state it's in now. Think about what that does. At first, the only state with a real value is the final winning board. That gets a big positive score. But over many games, that value starts to bleed backward. It propagates from the final state to the second to last state, then to the third to last, all the way back to the very first move of the game. This is how the agent learns not just what move is good now, but what sequence of moves leads to victory. It's a hugely powerful idea called temporal difference, or TD learning.
Now, an idea this powerful didn't just pop up overnight. And the book closes out this first chapter by showing how RL is really the child of two completely separate fields of study that for decades had no idea the other existed.
It's fascinating, really. On one side, you had psychologists studying trial and error learning in animals. Thorndike's cats and puzzle boxes, that kind of thing. And on the complete other side of the academic world, you had engineers and mathematicians working on something called optimal control, using really heavy-duty math like dynamic programming to solve complex optimization problems. For the longest time, these two rivers were flowing in parallel. Modern reinforcement learning was basically born when they finally merged in the 1980s. And that brings us right to the end, to this really provocative final thought. That tic-tac-toe agent, it learned to play a perfect game without any human supervision, without anyone showing it good moves. All it had were the rules and a goal: win. So if this simple loop of interaction and updating values can master a game, it just leaves you with this huge question, right? What are the limits? What else can an agent learn just by playing around in its world?